Thank you. Okay, so, oh, thank you. So first of all, thanks a lot for the invitation to this conference. It has been very nice. Okay, so I wrote down the title, and now I should also mention my co-authors. So this is joint work with Jeremy Blanc and Jego Jasinski. Okay, so I want to start with the definition of a Cremona group. So Cremona group of rank n over a field K is just a group of birational transformations that are defined over a field K of a projective space of dimension n. These are Cremona groups. And so this is an abstract group, and the structure of this group depends on the dimension of the projective space, and also there is arithmetic behavior when we change the field. And I'm interested in these kind of questions. And of course, more generally, one can study also just a pair of X, where X is some variety. And I'm interested in the case when X is close to being a projective space. So this is why the word Severi-Brauer is there. Okay. So first question. So I mean, okay, so this is a classical object, and there, so for example, Kostya in the first talk, he spoke about finite subgroups. Now I want to speak about generators. So this is like a first question. So one can ask, is here X, whatever X is it generated by involutions? Or more generally, is it generated by elements of finite order? And so the question about involutions, so Dolgachev has asked this for the Cremona group over the complex numbers. Okay. Then I directly want to state a second question. By the way, if you have any questions or comments, or if you can't see anything, please tell me. Don't hesitate to interrupt me. Okay, so now the second question is about quotients of this group. So I ask, what kind of quotients does beer X have? So another way to say this is, so I ask about group homomorphisms from beer X to a group G. And I ask like, okay, which G's can we have? And then one can also ask like, okay, for example, what if we ask G to be, let's say, abelian or finite? Or can G be large, whatever that means? Okay, so I asked like, what kind of groups can we have here as quotients? Okay, so let me give you some answers for the Cremona group. So when X is a projective space. So answer for when X is a projective space. So let's start with dimension 2. And let's start with the case when, so the classical case, so when K is an algebraically closed field. Okay, so we have the theorem of Noether-Castelnuovo. Which states that in this case, so for an algebraically closed field, we have the Cremona group is generated by PGL3 of the field and just one additional birational map, sigma. Namely, sigma is the standard quadratic involution. Okay, so this is given, let me write it in affine coordinates. xy is sent onto 1 over x, 1 over y. So we just have linear maps and one involution of degree 2. Okay, and now let me ask about, is it generated by involutions? Okay, so sigma is an involution. And actually, so PGL3, if you look at elementary matrices, you can ask your linear students from linear algebra to decompose them into involutions. That's they can do that. Or more conceptually, you can remark that because K is algebraically closed, this is the same as PSL3 of K, which is a simple group. Okay. But now when you take inside of PGL3, you take the subgroup generated by involutions. This is a normal subgroup. Okay, and so involutions exist, so it's everything. Okay. So this is generated by involutions. Okay, good. Now, what about quotients in this case? So first, let me tell you something, namely, we can write sigma, we can decompose them into, so it is conjugate, it is birationally conjugate to a linear map. So there exists a phi such that phi alpha phi inverse is sigma. I can give it to you explicitly. So take phi in affine coordinate to send xy on 2 x minus 1 over minus x plus 1, and the same for y. So y minus 1 over minus y plus 1. This should be an involution if I wrote it down correctly. And alpha is the map that sends xy onto minus x, comma, minus y. So this is alpha is a linear map. It is an element of PGL3. So we can decompose sigma into that. Now, why am I telling you this? Okay. Let's say we have a group homomorphism from the Cremona group to some group G. Okay. Now, inside here, we have PGL3. Now, when we restrict it, this homomorphism onto the subgroup PGL3, we get a normal subgroup. The kernel is a normal subgroup. PGL3 is simple, so the kernel is either nothing or everything. Okay. Now, if we say that G is not just trivial, okay, then this means the okay, so sorry. So either, sorry. So, okay, the kernel is a normal subgroup. So the kernel is either everything or nothing. Now let's look at the case now when PGL3 is sent onto 0. In that case, then also sigma is sent onto 0. Okay. Then in this case, then also sigma is sent onto 0, just because we can decompose it in this way. Okay. So this means that PGL3 injects into G, or the map is, or G is trivial. Okay. So now what does this mean? What can we say now about G? Okay, we know that it contains PGL3, but apart from that, I don't know how to describe this. Okay. Because it also means that, okay, G is not finite, it's not abelian, and also G does not have any quotients which are abelian or finite. So I don't know how to describe such groups. Maybe it doesn't exist. But they do. True, but let's say, yeah. Yeah. Okay, so what I want to highlight with this remark is that maybe the question about quotients is not a good question, because okay, but okay. But so we have the following theorem. This is due to Conte and Lamy. And they proved, so this was 2010, they proved that the Cremona group in dimension 2 has a non-trivial normal subgroup. Exactly, yes. It doesn't have any abelian quotients. Okay. But now this theorem tells us we have a normal subgroup, so we can quotient it out. Okay, so such G exists. But maybe the only way to describe this G is to say, okay, this is the quotient by the normal subgroup that they constructed here. So here in this case, we don't know what the quotient looks like. Now okay, and I also want to mention that this theorem is true for any field, and this was then done by Anne Langeau. So K, any field. Yes, exactly. Yeah. Okay, so now the situation changes when we work over perfect fields. Then we have construction of quotients. Okay, so I want to address this case. So still dimension 2, but now a perfect field. Now, okay. Okay, I don't know what to do. Okay, so
people in the time believe that it should be false. That's why I was interested that there was no evidence. People believe that there's no normal subgroup.
but I think the reason was more like because they were thinking of PGL, like in classical times, I think they were more thinking of PGL3, which is a simple group, so they didn't even believe that normal subgroups exist. Yeah, that's the. Yeah, there's like a, yeah. So this is like a 130 years ago, maybe something like that. No? 100. Yeah. No, 140, no? Okay, so anyways, so now if K is not algebraically closed, then we have constructions of quotients G. And the constructions that we have is that G is a free product of a direct sum of Z mod 2. So so here we have some indexing sets. I don't want to be precise. Let's say I and indexing set J. So all the quotients that we know are in this form. And there are different constructions. The first one was due to Zimmermann, then Lamy and Zimmermann did one. I also did one. And the constructions are different and they work for different kind of fields. But for any field that is perfect and not algebraically closed, we do have such a construction. Okay, and now this Z mod 2, this is now, so it depends on the construction. Yes, that's exactly, yeah. I mean, you can, for each field, you can feel the construction such that at least J is not trivial. Sometimes I is trivial for certain fields. Sorry? Yes. So yeah, except if K is algebraically closed. So maybe I should say not trivial. Yeah. Otherwise, it's anyways true. Okay. Okay. So now this Z mod 2, this is because in fact, so the first question that I asked about the generation by involutions, we also have this. So theorem, this is joint work with Lamy. We proved that CR2K is generated by involutions for any perfect field. Okay. And so here this set mod 2, this is because of the element, all elements have order 2. Okay, now let's go to a higher dimension. So you, yeah, so we use, so these constructions here, they use Sarkis of links, which are generators of the groupoid. This is the, yeah, and I mean, we say who survives. You will see this a bit later in similar fields. Explicit list. Well, what does it mean? So, okay. So the generators here are quadratic maps, automorphisms, Geisel, and Bertini involutions. No. No. I mean, this is already like if you have like over Q of the rational numbers. So, okay. So, for example, you can have a lot of different Bertini involutions, and you need them. Yeah, you have moduli. Yes, it's totally different. Yes, yeah. You really have infinite families also. It's no. If K is K bar, the only thing we know is there exist enormous subgroups, hence there exist equations. And with what I said before, we know PGL3 is inject. So. Okay, so dimension, larger dimensions. So now, okay, so if for the complex numbers, we have constructions where G is like it has the same form as here. So it is a free product direct sum of set mod 2 over some indexing sets. And here, so okay, there are also, again, we have different constructions. So the first one was by Blanc, Lamy, and Zimmermann. In this way, they proved actually that normal subgroups exist in higher dimensions. Okay, because they were able to prove that such quotients exist. And then there is also a construction by Blanc and Jasinski, so my two collaborators. And there is also a construction by Socrates, Tsikas. Okay, and then, okay, now something interesting happens. Now, if we have n at least 4, and maybe let me, if n is at least 4 and complex numbers, then due to Lin and Schindler, we also, they have a construction where G is Z. And in particularly, this implies that it's not generated by elements of finite order in this case. Okay, so dimension at least 4, Cremona group is not generated by elements of finite order. And here it's a bit more precise. They have a direct sum. I think it's the cardinality, right? Uncountable. Okay. Yeah, okay, let me. Uncountable. And also, so their construction, they use totally different methods from motivic, and they use a motivic invariant. And so their construction, it also works for n at least 3 and number fields. So for example, in the case when we have the rational numbers. But it doesn't work for n equals 3 and k the complex numbers. So in this case, we still don't know whether it's generated by involutions or not. So in dimension 3 complex numbers, we don't know. Okay, so let me just say maybe Yeah. Okay, and let me just say, so what they do in their construction is they compare the divisors in the exceptional locus of the map with the divisors in the exceptional locus of the inverse of the map. So this is the game they play. Okay. So I can state our results. So these results are together with Jeremy Blanc and Diego Jasinski. So theorem A, let S be a non-trivial Severi-Brauer surface. So thanks to Kostya that I don't have to explain what it is anymore. Surface. Okay, so non-trivial means that it doesn't have any k-rational points. Okay, now for D in 3 and 6, we write PD to be the set of the points of degree D. P point on S of degree D. And we do this modulo the automorphisms of the Severi-Brauer surface. Okay, so this is a notation. Okay, so I take the points of degree D, so of degree 3 or 6, and I take this set. Now the statement is as follows. Then, so we have at least, so the cardinality of P3 is at least 2. And for each, let's say, P0 in P3, there exists a surjective group homomorphism from the group of birational transformations of S, surjective onto direct sum Z mod 3, free product, big free product Z. And I should give you the indexing sets. So the direct sum is P3 minus 1 point, minus the point P0 that I chose in the beginning. And here the free product is P6. The indexing set is P6. K is a perfect field. They are automatically in general position. As Kostya has proved this. Yeah, this is a miracle that happens. It's the same is true. If they would be on a line, you would have a line. There's. It also has a point. And also, I mean, it doesn't. So for 3 points, general position doesn't means only that it's not on a line. Okay, so now, so here I said that the cardinality of P3 is at least 2. So I can take one out and I still have something in here. Okay, so I want to say, so this means that this group homomorphism is never trivial. But now what can happen is that P6 doesn't, so that points of degree 6 don't exist. So Kostya said in the morning that when the field is reasonably good, then points of degree 6 always exist. But there exists a field where it doesn't happen, and I want to give you an example. Sorry? Oh, over F2, you don't have any Severi-Brauer surface. Yeah, so that's also a thing. Not for all perfect fields, Severi-Brauer surfaces exist. Yeah. So remark.
I think that only 2 over 2 point of view system. But you need a point of view system to go to.
Okay, so P6 can be empty. Sorry, P6. What do I want? P6 can be empty. And you can take, for example, the following field. You take K to be the union over AB in N minus multiples of 3. And now you take a Puiseux series. So C of X1 over A. Okay, but this is not enough. You make of this guy, you make a Puiseux series Y X over 1 over P, and I guess it should be a Y. Okay, so so this was the easiest field that we found with this property. So I think Kostya was absolutely right by saying that reasonable fields have a point of degree 6. And so here the reason is that this guy doesn't have any even extensions. So it can't have points of degree 6. And so, okay, also a corollary of this theorem is that if a point in P6 exists, then BRS is not generated by elements of finite order. Okay, now we have also a theorem B, which is now in higher dimension, but over the field of complex numbers. So theorem B. For n at least 4, there exists a surjective group homomorphism from the Cremona group of the complex numbers to the following object. So again, we have a direct sum of Z mod 3, free product, big free product, Z. Okay, and the indexing sets are of something of cardinality of C. Okay, so so I wrote it in this way so that you see like, okay, they have something, there's some relation between the two. Okay, so I mean, of course, if you forget about this first part and just look at the second one, you can quotient out to get to some Z mod 3. So you could say, okay, we don't care about this part here. But what we have is that we have elements of order 3 that surject here, so that do not come from the quotient from here. So we can say something about the abelianization of this group. So we found that we have a 3 torsion in the abelianization. Okay, but from now on, I'm most interested in this part here, in the Z part. Okay, so this is the free group of a set of cardinality C. Okay, and now with this, we have a corollary. Okay, maybe I should keep it up. So corollary, let n be at least 4, and let G be any group such that the cardinality of G is at most the cardinality of C. Then there exists a surjective group homomorphism from the Cremona group of the complex numbers to this group. So this is an immediate corollary, just because here we have a free group of the indexing set of C. And now to answer the question I have in the beginning, what kind of quotients can we get? We can get anything, can get any group. Okay. So let me say a few words about the relation of theorem A and theorem B. So I don't want to make a statement about that. So because there is okay. What we need to do, we construct this group homomorphism, and there we do it for the complex numbers. Now I don't want to make any statement about the algebraically closed fields of characteristic 0. No. Okay, so the relation is we have okay, I take X over B, vibration with generic fiber S, and our construction is such that S is a non-trivial Severi-Brauer surface. Okay, with generic fiber S, non-trivial Severi-Brauer surface over the perfect field C of B. Okay, and now why? So okay, here I said we can only do it starting from n equals 4. So why n at least 4? And that's what I already mentioned before, because if the base is a curve, then we don't have any Severi-Brauer surface that is not just P2. So okay, because if dim B is 1, there is no non-trivial Severi-Brauer surface over C of B. Okay, so really we fail in dimension 3. And another remark, so that such a vibration exists where the generic fiber is a non-trivial Severi-Brauer, it's a subtle question, because Kresch and Schinkel they have constructed such vibration. So okay, there exist such vibrations where X is not even stably rational. Okay, and for our theorem, we need that X is rational. Sorry? Yes, yeah. Vibration that is not even stably rational. Okay, so this is just to say what is the connection between the surface case over a perfect field and the high dimensional case over the complex numbers. And also what I like here is that actually geometry over a perfect field can actually tell you something about, well, over complex numbers. Okay, but now I wanna give you the construction of the surface case. So if I will group homomorphism in the surface case, and then in the end, if there is still some time, I come back to this here. But if I don't tell you what the construction in the surface case is, there is no reason to speak about high dimensions. Any questions at that point? So what we use is we use the Sarkisov program. So Sarkisov links have already been mentioned in several talks before. So let me write it down anyways. So I write Bir-Mori of X. So this just means that we have the birational maps X1, X2, birational, where the Xi's are Mori fiber. So there exists, so they have a Mori fiber space structure, and Xi is birational to X. Okay, so this is a groupoid. And now the theorem is that this is generated by Sarkisov links. And isomorphisms. Okay. But actually we know more. We can also describe the relations between this set of generators. And the relations, I call them elementary relations. And we also need something which I call trivial relations. Good question. So the theorem holds in two cases. So either it's in dimension 2 and the field is perfect. So okay, then this goes back to Iskowski. Okay, so Iskowski was speaking about Sarkisov links, and now the notion of elementary relations. Okay, let me finish. So dimension surfaces and perfect field, or dimension of X is, okay, let's say at least 2, and K are the complex numbers. Okay. And now Haken and McKernan, they proved the Sarkisov program over the complex numbers in any dimension. Then Lamy and Zimmermann, they translated this back to dimension 2, but over perfect fields. So just like to say that the same machinery works for perfect fields. Okay, and then elementary relations, this first description of relations was by Kalogiros. And then Blanc, Lamy, and Zimmermann made slightly an adaptation. And then it's this is what I use. So the terminology of Blanc, Lamy, and Zimmermann. So let me say what are elementary relations. So for me, the groupoid is I also have the inverse direction inside. Yeah. Okay, so okay, now I give you the definition of a rank R fibration, which will encode the definition of a Mori fiber space, of a Sarkisov link, and of an elementary relation. Okay. And I will give you the definition for perfect fields, or so surfaces over a perfect field. Okay, definition. So for surfaces, so a fibration pi from X to B with connected fibers. So surjective. X and B smooth. Dimension of B is strictly smaller than the dimension of X. So this is a rank R vibration. If the relative pica rank of X over B equals to R, and B minus Kx is pi ample. Sorry, is it hard to read? Okay, so a vibration pi from X to B surjective with connected fibers. I recommend X and B to be smooth. The dimension of B is strictly smaller than the dimension of X. So this vibration is a rank R vibration if the relative pica rank equals R and the anti-canonical divisor is pi ample. And now, so now a rank R, a rank 1 vibration is exactly a Mori fiber space. A rank 2 vibration is exactly a Sarkisov link. And the rank 3 vibration will be an elementary relation. Okay, so let me remark or definition, or I don't know. So X over B is a rank 1 vibration exactly if it is a Mori fiber space. X over B, well, let's say maybe, okay, X over B is a rank 2 vibration, exactly a Sarkisov link. So to see this, can take the example. Let's say in P2, you blow up a point of degree 3. Now here you get a surface Y, which has a pica rank 2 over a point. So this is a Sarkisov link. So you blow up the 3 points and you contract the 3 lines through it. You go back to P2. And this here is now a Sarkisov link. Okay. The base is a point, yeah. So B is spec K. Okay. And now when I say rank 2 vibration, I mean Y over a point. Okay. Is it clear or not? Okay, and now X over B is a rank 3 vibration. And this is my definition for an elementary relation. So elementary relation between Sarkisov link. Yes, I assume that over my field, there exists a point of degree 3. Yes, yeah. Okay. Now the idea is the following. We want to construct a counting homomorphism. So yeah.
Well, the next step will be,
Yes. Yeah. Okay, so we will construct a groupoid homomorphism first. So we will construct something on the level of Birmori. And the idea would be that when we have, so first of all, let me say it in beginning isomorphisms, we send them onto 0. We don't count isomorphisms, but we want to count Sarkisov link. And the idea would be that if chi is a Sarkisov link, we want to count how many times does it appear. How many times does it appear? And the dream would be that we can go to a free product of Z. Okay, so that this would be the dream, like that we have no relations between the links. Then we can construct something very big. Okay, and so then this guy here is would be indexed by all the Sarkisov links. Okay, and so we would send this guy here onto the one indexed by chi. Okay, so this is like the idea. Okay, and now, for example, we can't do that. Like the first thing is that we have trivial relations. So trivial relations means that we have two Sarkisov links, but we can make a diagram with isomorphisms between them, so that they are basically the same up to isomorphism on the beginning and the end. And this, okay, so we need to consider this, and this means that we make an equivalence relation on Sarkisov links. So we say two are equivalent if they are the same up to an isomorphism. Okay, so here we have like these equivalence classes. So this is like the first thing. And now we have to check like, okay, what about the relations? Like, does it kill everything? Can someone survive? So we will go not to this guy here, but to some quotient.
Point on the left is natural to make homomorphism for the point on the right. Or maybe it would be less.
I don't know. I don't know. Okay, so now, now we need to know on Severi-Brauer surfaces what are the Sarkisov links. But thanks to Kostya, we already know. So there are exactly two types of Sarkisov links. So Sarkisov links on non-trivial Severi-Brauer. So either we are on S, we blow up a point of degree 3 and contract the lines, and we go to S op. Or we go from S, we blow up a point of degree 6, we contract the Galois orbit of the conics through 5 of them, and we go back to, well, we go to S op, with the opposite Severi-Brauer surface. So these are the only two Sarkisov links that we have. Now I just have to tell you, where do I send these guys? Yes, you're right. I don't have only two, but I have two types. Yeah. Yeah. Exactly. Okay, so the construction goes as follows. So we are in Birmori S. And okay, I mean, I've already told you where we will go. So we go to free product of Z indexed by P6, free product direct sum Z mod 3. Okay. So, okay, now let's say chi goes from S to S op, and it is of type 6, 6. Now we need to check, okay, and I want to send this guy here onto the one indexed by the equivalence class of chi. And I will send when chi goes from S up to S, right? Because these guys are also in Birmori. When I go from S up to S, the other way around. Now this guy, I send it on to -1 of chi inverse. So what does it mean? It means that in the indexing set, I only have points on S. And this is important, that I can distinguish between S and S up. So I only take the points on S. Okay? So in this way, I can go to 1 and to -1, because I need this such that the trivial relation, which is just chi times chi inverse is 1, that this is satisfied. Okay. So this is okay. Okay. And now we need to know what are their relations and which kind of relations do they appear. Now in the elementary relation. So okay, this means we have S over a point is rank 3, but this means let me so this means it's a Del Pezzo surface. So rank 3 vibration has to be a Del Pezzo surface because it's just over a point. Okay. Now, what kind of can we get a Del Pezzo surface over the blow up of a point of degree 6? We cannot, because all the points on S, the degrees of these points are divisible by 3. Okay, so we on up here, we can't blow up a rational point or a point of degree 2 because they don't exist. Okay, but we can blow up a point of degree 3, but then we are out of the Del Pezzo world. Okay, so here we do not have any elementary relations that involve such a link. And this is why we can go to Z, because there are no relations that involve in this link. So no elementary relation. Because all points on S have degree divisible by 3. And this is why we can go to Z. So this is an element of the copy of Z. Okay, and now for the point of degree 3, we do the same thing, but there we will have relations. We will have relations because we can blow up a point of degree 3 and another point of degree 3. This gives us a elementary relation. Okay. But we can look at this this relation that we get, and we will see that we will go to Z mod 3. Okay, so let's say similar for S op 3, but there are relations. Are there questions to the surface case? Sorry? You want to go to a conic bundle? You cannot. I mean, also, I mean, if you believe in the Sarkisov program, you can find all the. I mean, you can also check like what are all the Sarkisov links that start on S. So you can only blow up a point of degree 3 or 6. Yeah. Okay, and now that so now I can say 2 minutes something about. I can go back to going to higher dimensions. Okay, so this is the construction for the Severi-Brauer surface. Now, how do we go to the high dimensional part? I made some notes this morning. Okay, so we have so now I will be very vague. So you can complain or not, I don't know. But okay, so the theorem goes something like this. We have X over B, a vibration, S generic fiber over C of B is a del Pezzo surface that is not birational to a conic bundle. Okay. Now, let Mx be a set of good links, of good and compatible links. So Sarkis of links on X. So just like it means in Biamori X. So maybe I should write this. In Biamori X. Okay. Of type 2. So it means with structure of a base. Type 2 of large covering genus. I mean, I'm hiding a lot of things. I mean, I'm also not saying what is good and what does compatible mean, but it is over a base. So wait. I'm not finished. Covering genus such that they induce good links on the generic fiber. So yeah. Okay, and let me call the set of links that we obtain in this way. This will then be MS. Okay, now, if there exists a groupoid homomorphism Biamori of S to some G, such that only elements of in my set here in MS survive, then there exists a group homomorphism Biamori of X to G. So this is the theorem. I'm not saying what is good, what is compatible, what is good here. The only guys that I don't kill, so that are not sent on to 0.
Are contained.
Yeah. No. Okay. Yes. And I can give you the proof. And I mean, okay, it's the proof is okay. Actually, I don't remember how many pages, but I mean, anyway, the paper is long. So the idea is the following. So we use. So with the BAB conjecture, we know that because here we use we have this large covering genus. With this, we know, well, we know that we don't have too many relations. Basically, what we can say is that the elementary relations that we have, they are over the base something of codimension 2. And we don't have, there are not other, like we don't have to go to very small codimension, because that's then very difficult and there is a lot of stuff. But in this way, we know we can only look at so such links are only involved in a few types of elementary relations. And then we classify them and check that we're still good, that our group homomorphism survives. Okay, sorry, I don't have more time.
Any questions?
We know something about the kernel of the
In theorem A. The kernel, I mean, actually, the kernel should only automorphisms. Should be exactly automorphisms, because all the other birational. No. Okay, I mean, okay. No. Okay. No, there are more.
Is there some relation of length?
No. So the thing is, because we have like, okay, when we have a point of degree 3, okay, the equivalence, so the modular automorphisms of S, this means that if they have the same residue field, then they are isomorphic. Then they're equivalent. So if you just do one, so okay, if you do the blow up of a point of degree 3 with the residue field, and then later you do the same, a different point of, but with the same residue field, this will cancel out. Yeah, but it's not the identity. So I don't know what to say about the kernel.
I think it will have a long relation of lenses, right?
Yes. But
6 links.
yes. Yeah, so this is why here we go to set mod 3. Yeah. And which is sent onto 0.
Other questions?